So we're trying to work out the EMF of a cell. We have 4 different circuits that we could potentially use. We're plotting a graph of terminal PD against current, voltage against current, whatever the voltmeter reads against current. And then we're trying to figure out which one of these circuits would give us a y-intercept of the EMF. So I'm going to go over a bit of fundamental theory first before we look at the options. So let's think about a circuit. So it's a simplified version of the circuits that we have above, where we just have one external component. So let's just say we have a variable resistor. We have an ammeter. This is our cell. And we have an EMF of epsilon. We have a voltage across our internal resistance. I'm going to call that V int. And a voltage across our external load, which I'm going to call V term, which is the terminal PD. And let's say the resistance of this is lowercase r, the resistance of this is uppercase r. Okay, and then so if we think about how voltage is distributed in this circuit, we can say that the EMF is equal to the voltage across the external load or across the terminals of the cell, and that's the terminal PD, plus the voltage across the internal resistance. And there's a few ways we can write this equation. We can write this as current times the external load plus current times the internal resistance. Or we can write that as, well, this is usually just written as V. So V plus I lowercase r. They're all different ways of writing the same thing. In terms of the graph that we'll be plotting, we'd plot the voltage that we measure on the y-axis and the current that we measure on the x-axis. Oh yeah, forgot to draw the voltmeter. So we also have a voltmeter right here. So that voltmeter is in parallel with the external load. It's also in parallel with the cell. So this equation here, if I change the order of that, if I write it as, if I make V the subject and write it in this form, so I've just basically brought the this quantity to the other side. This is of the form y is equal to mx plus c. So our minus r would be our gradient, I would be the x value, the EMF would be c, and then v would be the y coordinates or the y values. So then when we plot this graph, our y-intercept should be the EMF, and our gradient should be the negative of the internal resistance. And if we look at this bit here, the voltage that we have on the y-axis, so the terminal PD, is equal to the current that's going through the circuit, so the current that's being drawn from the cell, multiplied by the external load. So yes, this has to be, that's a key thing to distinguish the correct answer in this question. This is the current being drawn from the cell that's going through the entire circuit, and this is the resistance of the external load. So let's look at our options. Remember that the voltage that we measure, that we plot on this graph, it has to be the terminal PD. It has to be the voltage across the entire external load. And for that reason, it can't be B. It can't be B because this just measures the voltage across the variable resistor. It doesn't measure the terminal PD, which is the voltage across the entire external load or the cell. Let's look at the 2 parallel options. So the voltage that's measured in this case is the voltage across this component, and it's the same thing here. So both of these scenarios measure the voltage across the fixed resistor. And because the fixed resistor is in parallel with the variable resistor, then the voltage that we measure across the fixed resistor is the same as the voltage across the variable resistor. Or in other words, the voltage that we measure is the PD across the external load, the entire external load. So if we think about this equation here again, where we have our terminal PD is the current through our entire circuit multiplied by the external load, we are measuring the voltage across the external load, so that is good. But the problem with those 2 circuits is that the current that we're measuring is not going through the external load. It's only going through part of it. So this current is not the current that's being drawn from the cell. It's just going through part of the circuit. If our ammeter were placed here or here in either of these scenarios, that would be fine. That would be a fine way of doing this. We have a way of varying the external load, and then we can see how the current and voltage respond to the external resistance changing, and then plot our graph. So that's the problem with C and D. The fact that the current is not the current that's being drawn from the cell. It's only a current going through one of those two parallel branches. So it can't be those two. It must therefore be A. So for A, we do have a means of varying the external resistance. The voltage is the voltage across the entire external load, and the current is the entire current that's being drawn from the cell, not just part of it, which is what we have in scenario C and D.